Right, hi everyone. Inverse trig this time. So C3 inverse trig. You know what inverse functions are already. We've talked about inverses. And the same logic would apply for the inverse trig graphs. Inverse trigs doesn't come up that often, but it did come up last year. But before that, it didn't come up much. But remember, we're not learning for exams. We're learning to stay sharp, investigate everything we can about maths, uh, and then we can draw on it later if we need to. So, sketch the inverse trig graph specifying the domain and ranges of each. What do the inverse trig graphs look like then? So let's think about it. Here we've got our sine x. So here's sine x, and whoops, started to draw cos. And we know that this goes between here and here like this, don't we? But what do we say about inverses? Inverse functions, so if this is pi by 2, pi minus pi by 2 minus pi, inverse functions only exist if 1 to 1. Okay? At the moment, this is not a 1 to 1 function, is it? This is a many to 1. So I need to restrict the domain of my sine graph straight away. Straight away, I need to restrict it. Now, this is a 1 to 1. Fantastic. And we're happy. And remember, this is at the point -1 and 1 for its maximum, yeah? So how do we draw an inverse function? Remember, we draw it by reflecting in the line y equals x. So all the x's and y's flip over. So the x of pi by 2 now becomes the y of pi by 2. The y of 1 becomes the x of 1. And the minus pi by 2 becomes your y. And your minus 1 moves over here. So now everything is reflected the other way. So if it's reflected in that line, this thing is going to peak like this, isn't it? And it's going to come out like this. So it's reflected about the line, and you've got to be real careful that your gradient doesn't look like it's becoming a straight line. It's got to look like it's tending towards infinity, right? So there you go, there's your arc sine. This is y equals arc sine x. And arc sine is a fancy way of saying sine to the -1 of x. And that does not mean 1 over sine x. That's just a way of saying inverse sine x. So this is the same as inverse sine x, okay? There's your first graph. What about cos x though? So now we've got cos. There we go. So 0, pi by 2, pi. Again, this is a many to one function, which doesn't have an inverse. So we have to restrict the domain again. So notice here, I also need to define my domain. So if f of x equals arc sine x, our domain clearly, all the x values it can take is between 1 and -1, whereas our f of x values, you can see, range between pi by 2 and minus pi by 2. This one, for cos, I would have to restrict it. I could restrict it anywhere, really, remember, because these things goes on for infinity, but convention is to take the first positive branch. So this is the first positive branch here, where we don't cross over, because remember, the moment I go over that turning point, I've got a many to one, because I've got two values of x giving me the same y value. So this is the bit I care about. Reflection in the y equals x graph line will then produce, and then here we go. So this was 1 and 0. So we swap them over, so now our x value is 1. Here was pi by 2, and it gave us a, so pi by 2 on the y gave us a y of 0 gave us pi by 2, so we have to swap that round. So now we've got a y of pi by 2 give us an x of 0, so that means we know it crosses here. And now we've got this last bit at pi, which gave us a y value of -1, so now we've got an x value of -1 and a y value of pi, so that's going to be up here. So here's pi, there we go. If it's inflected in that graph, this thing's going to switch round, so actually it looks like that. Right? So it cuts off at the two turning points here. And again, we need a domain in range. So our domain, if f of x is arc cos x this time, our domain is going to be between 1 and -1 again. Okay? And also we've got f of x, ignore that. F of x, you can see, is its y values. This thing doesn't go lower than 0, and it doesn't go higher than pi. So there we go. There's our graphs. We also need to do the version of tan, so arctan. So let's have a go at that. So if tan looks like this, right? Like here, asymptote here, pi by 2, asymptote here, minus pi by 2. Again, you can see at the moment this is, well, A, it's discontinuous, so it's not a function across all of the values of x, and it's a many to one again, right? So many x values give the same y value, so we have to restrict our original domain. We can only take one branch of it to make it 1 to 1. So that's our branch here. And here, remember, this thing tends to infinity and minus infinity. So if we invert it by the line y equals x, yeah, y equals x, then we're going to get, where we had an asymptote at pi by 2 on the x, we're going to now have an asymptote of pi by 2 on the y, because all the x's and y's switch over. And minus pi by 2 equals y, y equals pi by 2 here. You can see here that this thing crossed at 0, so this will cross at 0. And also this stretch to y infinity, so now it's going to stretch to x infinity, and here we go then. So there's our curve, like so. And that is our f of x equals arctan x, and our domain, well, our domain, you can see, is all x values. So x is all the reals, and our range, well, f of x doesn't actually hit pi by 2, does it? Because it's an asymptote, and it doesn't hit minus pi by 2. It's just shy of these asymptotes. That's why they're called asymptotes. So that's why our inequalities are not inclusive. So they're the graphs. How do we actually use this stuff in questions? And these questions are pretty fun, I think. Remember what arc cos means. Arc cos means cos to the -1 of x, doesn't it? So inverse cos. And remember what cos does. Cos says, give me the adjacent over the hypotenuse, and I'll give you the corresponding angle. So therefore, arc cos says, give me the angle. Sorry, cos says, give me the corresponding adjacent over the hypotenuse, yes, and I will give you the angle. Arc cos says, give me the just done it the wrong way around. So cos says, give me the angle, and I will give you the adjacent over the hypotenuse. Okay? Sine says, give me the angle, and I'll give you the opposite over the hypotenuse. Okay? So arc cos says give me the opposite, sorry, the adjacent over the hypotenuse, and I'll give you the angle. Just like arcsine says, give me the opposite over the hypotenuse, and I'll give you the angle, right? So had them all the way around. It's easy to do. So cos says, give me the angle, I'll give you the adjacent over the hypotenuse. Arc cos, the inverse, says, give me the adjacent over hypotenuse, and I'll give you the angle. So how do we work this stuff out? Arc cos 1 over root 2. Well, that just means in your calculator, isn't it? So that's cos to the minus 1 equals that. But I could say, let z equal arc cos 1 over root 2, right? And therefore you could cos both sides and say cos z equals 1 over root 2. You see the relationship between the two? You can cos both sides or you can arc cos both sides. But arc cos 1 over root 2, I think we said it in a previous video, and you should know it anyway, is pi by 4. And remember, as it's a one-to-one function, an inverse function, you're only going to get one solution. If you have tan to the minus 1 0.3, what you're saying is this is in the form of f to the minus 1 of x equals x, isn't it? Because you are tanning, well, first you're inverse tanning 0.3, and then you're tanning it again. So what are you left with? You're just left with 0.3, yeah? This one, though, you got cos of sine to the minus 1, 2 by 3. How can you deal with something like that? Well, again, it's good to say z equals sine to the minus 1, 2 by 3. So it's interesting to kind of work inside out, like functions. So here you can sine both sides. Do you see? All right? So now, as you're saying z equals this, we're looking at cos z, right? And sine z equals 2 over 3. And what is sine? So z is the angle, like we said earlier. Sine is the opposite over the hypotenuse. So from here, you can find out what the adjacent is, because you can use Pythagoras. So the adjacent is the square root of 3 squared subtract 2 squared. So this is root 5. So this is root 5. So let's go back to the original question. What was cos z? Well, cos z, you can see, is the adjacent over the hypotenuse, root 5 over 3. Ta-da! Really nice. Let's try that again, but with sine tan to the minus 1x. So again, if you let z equal tan to the minus 1 of x, you can tan both sides, and you're there. So actually, we're looking here at sine z, where z equals tan to the minus 1 of x. I tan both sides, so let's draw that. There's z. Tan, remember, is opposite over adjacent. So this x is the same as x over 1, isn't it? So that's 1. So through Pythagoras again, you can find what the hypotenuse is. So h is the square root of x squared plus 1, isn't it? Or 1 squared, if you want to say that. So that's root x squared plus 1. Go back to the original question. What's sine z? Sine z is opposite over hypotenuse. So x over square root x squared plus 1. And you're finished. So these problems are really fun. If you work out the triangles like that. Give it a go.